good evening, good afternoon, depending on good morning as well, depending on where you are on the planet. And thanks to our speakers today. This is another Roast and Tell day. So just like we usually do, I will go and introduce myself. So me as the co-organizer here with Yaneri. I'm a Rostasian from Guinea, Republic of Guinea, that is in West Africa. And I currently work as a ROS developer for a company called QuickWit. QuickWit, we are developing a search engine big by object storage. And we are also the company behind TenTV, which is a ROS search library. So if you have time, you can probably check on GitHub what TenTV is and what it can do if you are interested or if you need search functionality. So this meetup has a lot of support from Jan Erik and Bastian and Brian Levitt. And this meetup is intended for beginners level to expert level. We are here to share our struggles, ideas, and hacks and projects. So Roast and Tell is a space for the community to learn and grow together. And we expect you to also participate and help us in any way, especially through coming up and speaking here at this meetup. We follow the Code of Conduct from Berlin, and if you want more info on it, you can go to berlincodeofconduct.org. If you see anything inappropriate, you can privately or directly report to us, me via email or our Twitter handle, or Jan Erik, or via email the same, or his Twitter handle. So this is an online meetup, so we have it available here on Zoom, and then we also have the Zoom chat where you can post your questions. We currently have 3 talks. Between those talks, after the second talks mostly, we will hold breakout rooms. This is an opportunity for every participant to talk to each other and then sympathize with each other. It will last 15 minutes, and after that we can come back for the last talk. If you will be randomly assigned to breakout rooms, so if, for instance, your room becomes empty before the end of the 15 minutes, you can come back onto the main room, and we will always be able to assign you to another room. We also have matrix chat available where you can post your question, and then this is live stream on YouTube as well as on our website. Again, as a reminder, you can type your questions here on the chat, or you can post it on Matrix chat. Another thing we really care about is that we want you to come in and speak at this meetup. We always have 3 spots, so we expect you, and we feel like this is a good place to share your knowledge, your experience on any level you have with Rust. So today we have 3 talks. And the first one will be from Tim, 5 tricks for beginners to learn Rust. Tim is a software developer, a data scientist, an artist, and a technology writer, and he is the author of the famous Rust in Action book. The second talk will be ergonomic error handling, and the third one will be building a cryptocurrency derivative exchange with Rust. So without further ado, let's start with Tim. And
wonderful. Okay. Thanks very much for the introduction. It was very kind. I'll just share my screen. So there should be a big white box in front of you now. Perfect. How does one start these things? Schönen guten Abend, mein sehr geehrter Damen und Herren. or something like that. I used to be able to speak German. These days, not so much, but I miss Berlin very much. I'm currently speaking to you from New Zealand. If I make mistakes, please accept my apologies. It's currently 7 past 5 a.m. Here in Wellington. Okay, cool. Where do we go? We are going to be doing a beginner talk today. And like normal, we start these things with a bit of an introduction about who I am. I see myself as a mentor in the Rust community. Follow me on Twitter, YouTube, and Twitch for I organized the Rust Wellington meetup group. Luckily, we are COVID-free here in New Zealand. We haven't had any cases, I think, for well over 6 months now. So yeah, it's actually an in-person meetup, which is interesting. As Ivan said, I am the author of Rust in Action. Day to day, I do data science. Actually, I am particularly focused on data engineering and at a small consultancy, well, actually a large consultancy called Dragonfly Data Science here in Wellington. Okay, about the talk. I want to reiterate one thing to emphasize is that these are not the most common traits. This talk is designed to inform you about how Rust feels like as a programming language or how it is implemented. And so my intention is to be able, if you have only used Java or C# or Python or JavaScript, to be able to understand a little bit about you're having difficulty with Rust. My intention is for you to be able to get an understanding for what's happening inside Rust. And traits are essential to how it operates. So for those people who don't like listening to long talks, I have a 20-second version. Partial equality is the trait the trait that relates to the equality operator. All operators are implemented with or are defined by traits. Display is how you ask a type to convert itself to a string so that it can be printed to the console. Clone is a mechanism for being able, from the beginner's perspective, to avoid the borrow checker while you are understanding or taking the time to learn ownership. The iterator trait is one of the first steps for being able to really understand how Rust is slightly different from other programming languages or its peer languages, in particular sort of C++. And this provides this very, very ergonomic or very friendly way of using a for loop for any collection. Deref is this ability for the dot operator, so method calls, to be able to automatically call methods that you can deref into. And that sounds very confusing, but it basically allows, if your type can dereference itself to become another type, you can call the target type's methods from the parent type itself. So that's the 20-second version, probably a bit more than 20 seconds. If you have started with Rust, or you're just very, very new, a struct is just a type which can be composed of multiple objects. So it isn't the same as a class, but it's very similar. But you can think of it as a plain object. So we create them with, so here I'm defining, oh, sorry, it's saying that ignore this error. It's saying that it doesn't know how to, I can fix that. I can define a cube and also create one. But there are no methods attached to this struct. Okay, and the other thing that I want to just spend 10 seconds talking about is the notion of a bit pattern. And this will become important when I describe something about floating point. And it turns out that just the term bit pattern means a sequence of bits that represent a type. It is the internal representation for every type is at some stage turns into a sequence of zeros and ones. And that's what I mean by the term bit pattern. Okay, so now we are ready to talk about what a trait is. Traits are the foundation for all behavior inside Rust. And it's the foundation for all behavior that is shared between types. So if you have all floating point numbers or all integers behave in a similar way, even though they are different types, and that is enabled through traits. You can think of traits as being an abstract base class or an interface. If that might be helpful if you're from an object-oriented language. So almost all of Rust is actually built with traits. Operators, methods, the generic system is, and trait objects are all connected to traits in some way. So for example, as I mentioned, addition is defined by this trait, which is standard ops add. So for example, I can define I can import the trait add. And if we ignore what we say is that this triple function will work with any type T that implements add and the output of the addition is the same type. Oh, and by the way, it must be copy, which means that type T will copy itself instead of basically duplicate itself if it needs to, if it was going to encounter any borrow problems. And what happens if we've seen Rust generics before, so I can call triple with a floating point number, or I could call it with an integer, and it will quote unquote just work, which means that I have defined one function in source code and use traits to be able to specify that it must be a type that implements addition. But for some types many types don't implement addition. And so you cannot add a string slice to another string slice, and the type system will protect you from doing things that are illegal. And it's all enabled by traits. So how do we define them? Well, a trait, in this case, movement, is defined by a set of methods, and the distinguishing characteristic, they look a lot like a class without any data. And structs look a lot like a class without any methods. And so I've got the struct here with node members. So it's just what we call a zero size type. And a sentinel in English is just a thing that never moves. So I'll just define movement here, sentinel, and but a cannonball, let's say, implements movement. It can't change its direction once it's fired. And so if it's in the air, it can only change its speed, let's say. And so the trait system does not impose any more restrictions apart from the type. It can be a little bit more sophisticated. We saw the output thing, but in general, if you define a trait, you're free to implement it however you want with whatever type that you have. This was a little bit confusing to me because I sort of thought that that these definitions were slightly more magical. That if I had a trait like movement, that I would expect it to always be moving, but actually it turns out that you can implement it just with doing nothing. Hopefully that makes sense. Okay, right. One distinguishing characteristic is that traits do not have data. So we can't say that the trait movement requires that the type has a speed attribute and a direction attribute. It doesn't make sense from Rust. Traits only relate to methods. Okay, so now we get to our first trait that we want to discuss for beginners, clone. And the reason why I think this is first is that if you're a beginner, have you ever seen this use of mood value or something related? I feel that it's okay to spend a little bit of time at runtime cloning values if you're spending hours and hours and hours learning Rust. So this is my example. So I have this function save, which is supposed to save an object or this vector of integers to disk, let's say. And so here's my list of my vector of numbers, and I try and save it once. And so this is just a read-only method. And then I mutate or modify the value. I add 2 extra elements, and then I save it again. So Rust, when you start, will give you this horrible error. And it turns out that one way to fix this is by asking for a read-only, or what we like we can take a reference to it. But another way to do it while you learn, it's complicated. So we've got this shortcut, which is we can add a clone method. Clone will duplicate all the values, and this one will, I hope, work correctly. And in this case, it actually does. So I'll just do that once more. Oh, okay. So now I'm getting a different one because, so just the way that the execution environment, it's already used save, and so it thinks that the last call that I just executed is still present. So I can create a new variable, and that might work. In fact, I can't do it there either because save, I'll need to clone it twice if I want to print it out. Oh gosh. Ta-da! Okay, perfect. I should stop playing. How do I implement clone? So this is the cheat way. So I've got these 3 structures, three types, and I need to implement clone for them. So how do I do so? In particular, I really care about this meeting thing. You actually saw me using a derive attribute earlier, which is a request to the compiler to implement things on our behalf. And now that's it. Whenever many types in the standard library already know how to clone themselves, and so if you have a struct that only includes members that already know how to clone themselves, which is the majority of cases when you're starting out, then you just need to derive clone, and then you will have access to a clone method, which is quite handy. Okay, partial equality. All operators are defined as traits, and we take 2 values, left and right, and we return a Boolean result. And so that's fine. But the question is, well, why is it partial? Like, that sounds very strange. And the reason is that Rust tries very hard to get things right, or model the environment, model reality as accurately as possible. Rust is very precise. It is a systems programming language, which means that it really cares about details. So floating points take a bit pattern. You can see here that we have 2 floating point numbers with different bit patterns. This one's 0, and this one's, 2 to the 32 minus 1. And they both evaluate as true. So there's 2 bit patterns that are not the same that evaluate as true. And we have here the same bit pattern on both sides. And if we try equality, they evaluate as false. And so if you haven't encountered this behavior, it might be worthwhile just for me pausing to explain what's actually happening. Floating point has so I'll just cheat a little bit, has the notion of a -0. So this is 0 with the sign bit sign bit flipped. And so both 0 and -0 evaluate to are the same numeric value, and so they evaluate to true when for equality. Now this one here, so that's that first example. The bit pattern is a bit sneaky of me. So by the way, just to prove to you that this is a, oh no, I shouldn't, I'll just stick. So F32 nan. So what the heck is that? Floating point has a representation for in fact, many bit patterns that evaluate to a result from expressions that are mathematically undefined. So for example, division by 0 is one of them, or like division by infinity, for example. And so the partial equality exists for floating point because of these very strange circumstances. And this is what I mean by one of the things that to understand about Rust is that it is pedantic and precise. Okay, display. Display is very practical because one of the first things that you want to do when you start out with programming is print things to the console. And one thing to note, however, is that display is different from debug. Oopsie, that's marked down. The debug trait is intended for programmers, whereas display is the trait that you will use if you want a string for users. There is also a subtle link to error handling, but let's ignore that. So ich bin ein Berliner relies on if I want to print that to the screen, I use the display trait, and the syntax here uses the debug, which is the programmer specific representation. So this question mark is debug, and just curly braces is display. Now, how does one implement display? So I've got a place, let's say a city. Let's change it to city. That has a location represented as a coordinate and a city name. And then I want to implement display for city. So I need to implement I bring the trait into local scope. And it includes one method, which takes the strange type formatter with a kind of anonymous lifetime. And the easiest way to implement display is to find some member of your type that already implements display, and to just use that, rely on that member. So, for example, let's say I'm only relying on the name attribute. I'm actually ignoring coordinate for the purposes of display. Excuse me, conflicting implementations. That's a bit strange. I wonder if this is a problem. I think I pushed enter twice. And so I'm actually not sure where Berlin is. But if I said that, you know what, we'll just say null because that's easy. It's off the West Africa. And then I want to print it. Berlin. Oh, expected it. Oopsie, it's all gone wrong. Okay, there we are, City Berlin. Cool. That's me implementing display. Okay, deref. Deref is quite special. It allows types to become other types. And if you encounter any confusing behavior with Rust, this may actually explain why. Rust supports the notion of a auto deref. And so for smart pointer types, deref provides access to the inner type. Here we have a box of string slice, and the deref operator, which is the star thing, actually returns the string slice itself. So I say this is the, text is the wrong type. It is a box, but we've asked for a string slice, and I can use the dereference operator to access what's inside it. But more magically, it will actually, the dot operator, which is the method, how we call methods in Rust, will automatically deref things if the target type supports the method. So for example, I've got this Plattdeutsch string here on one moin, and I used to live in North Germany, so maybe that's a dumb joke. Okay, anyway, so string does not implement make ASCII uppercase, but string slices do. Occasionally, you will encounter some kind of counterintuitive syntax. So you see the dereference operator followed by the reference operator and then type T. This looks like it should do nothing. They should effectively cancel each other out. But what is happening here is that we're taking a reference to T, and that type, the referent, might implement something else with deref. And so it isn't purely working. If you've only used pointers before, just remember that Rust is doing something more when it dereferences values. It's actually relying on the trait implementation. And every trait, every type can define exactly what it means by every trait. So just as we had movement for Sentinel did not actually move the Sentinel, here we have a dereference operator, which isn't actually dereferencing a pointer. It's just doing some conversion. So here's some syntax. Oh, so here's some wording from the Rust reference, just saying that on non-pointed types, star x is equivalent to star of dereference of reference to x. So yeah, I'll just leave that actually. The last trait that I wanted to talk, I think this is the last one, is iterator. So it enables us to go through for loops, and that's nice. So one question is, how do we want to be able to implement, we want to be able to create a year from season. And so how do I do so? Well, I start with, I've got, the way to implement iterator is to create a sister type, a type that it lives alongside. If I've already got one implementation, excuse me. And this has already been evaluated. So oh man, gosh. This did work just before when I was testing it. That's really perfect. Excuse me. I'll go back. I should maybe, so now I've got a year method on season. I'll go back to describing what's happening here. So in current season, I yield every iteration, I return an item, which is the season type. So kind of like the sister, the internal part of season. And every iteration I check, like what follows summer? Well, that's autumn. And what follows autumn? Winter. And then I mutate the internal state, and I return the next, I return the next item. And I apologize for this stuff at the bottom. It's just because I implement it twice. And so the other thing that I need to do is tell season that on the into iter method that I should convert myself to the sister trait, sorry, the sister type. So what is happening in a for loop is that the for loop is actually iterating or calling a sister type of whatever you're iterating over. So inside the definition of year, we are asking season to call into iterator or into iter, and then that is being used to create an iterator. Okay, cool. Right. I don't know if we have any extra time. I think I'm about at 20 minutes. Sometimes traits have nothing, no time, no methods, and they're called markers. And my favorite implementation is assisted mem drop, which is just defined for every type. There is actually no contents at all. I think this is so what's actually happening is that drop, like deref, acts as an operator implicitly, and will just call the drop method on the type when it ends this its scope. Okay, and I'm finished. Thanks very much. I'm more than happy to receive questions. Hopefully you enjoyed the talk.
Yeah. Right. Thank you, Tim. I think we have a few questions. Great talk. The question is that a Jupyter notebook used for the Rust code?
Yes, it is actually a Jupyter notebook being used for Rust. So there is a Rust kernel for the Jupyter notebook. So if you search for Rust kernel Jupyter, you will find it. I can also post the link, and I can. It's got a very strange name. I'm just searching for it now. It drops executed at the end of scopes. Oh, sorry. Oh, sorry. I just saw the problem with the font. I apologize, Jan Erik. I probably should have, made that question. So yeah, okay. Thanks, David. David has just posted a link to the Rust kernel, which is in the Google namespace under GitHub. And the other tool that I was using for turning it into a presentation is it's called Rise Slideshow. And I can give you the link to that also. So I apologize if the text was too small. Hopefully things are still legible.
Yeah, it's all right. I don't see any other questions for now. If you have questions, please just post it.
Perfect.
Now. All right, so with that, thank you, Tim. And if there are further questions, probably you can check on the chat. We'll move on to the next talk. That's going to be given by Senyo. And he's going to be talking about ergonomic error handling in Rust. Senyo is a software engineer with a focus on infrastructure. Before that, he worked as a data scientist building computer vision model. So currently he lives in Cape Town and he works for a startup and that building the next generation of smart technologies for agriculture. Senyo, up to you.
Awesome. Awesome. Thank you, Evans, for the introduction. Yeah, cool. Very excited for this. Yeah, so my talk is on ergonomic error handling with Rust. So just kind of like overview of where we're going. So yeah, initially just an overview of error handling in Rust, kind of like, yeah, just how it works and the mechanics. For the veterans, will probably be pretty standard and boring. And then going on to like making error handling ergonomic and how, yeah, Rust just tries to make the whole process ergonomic, and then going on to making errors informative, and then just the future of error reporting and you know, what the kind of like where we're going with error reporting. So, I mean, Evan's already introduced me, but yeah, I'm a software engineer. I work on the platform team at Aerobotics. So yeah, working with infrastructure. And we're an agri-tech startup based in Cape Town, South Africa, and passionate about technology and how we can leverage it to improve the world around us. I write semi-regularly at senyosimpson.com, and you can find me on Twitter posting annoying tweets at Senyusis. This is just a picture of Cape Town. I just thought I'd show everyone what it looks like. This is a sunset at one of the places we call Sunset Rock. Yeah, I'm sure all the Europeans are jealous. Awesome. So getting into it, why is error handling important? So yeah, the most important thing I want to just emphasize through this talk, and like the biggest takeaway, is that error handling is really just about communication. And yeah, just being able to communicate to developers what's going on, you know, why it happened, where it happened, et cetera, et cetera. It's really just about communication. But some other things that are important. So it prevents undefined behavior. So we don't want our programs to continue executing if they're, you know, in invalid states or ill-defined states. Provides context to failure mode. So this is just, again, about communication and providing the requisite information. And makes developers happy. Who doesn't want happy devs? Cool. So how Rust does error handling? Rust has no exceptions. And instead, errors are returned. So it's similar to Golang in that paradigm. And it takes inspiration from the ML family of languages, so different from Golang, and it adopts the result type for handling recoverable errors, which I'll talk through later in the slides. And yeah, irrecoverable errors are signaled using panic, again, which I'll go through. So recoverable errors, these are obviously errors that we know how to handle. And you know, in the course of program execution, we kind of like come across circumstances which we know what to do and how to handle them correctly. So a good example, for instance, here is, you know, if you want to read a file and you don't have any expectation on that file existing, that's an error that we know how to handle. So the result type is how we sort of like denote fallible computation or fallible functions in this case. So a result type's an enum, which has two variants, OK and error. If the computation succeeds, it returns or it contains the value from that computation. Otherwise, it contains an error. And this is really, it's nice and super beneficial because we get a quick view into the fact that like a function is fallible just from the function signature. So, you know, again, it's about communication. And we're easily able to tell like, okay, you know, if I run this function, I'll have to handle the error if it crops up. And then again, it also forces us to handle those errors. Awesome. So just like an example of using results, so we create this file, ferris.txt, and that returns a result file, obviously if it succeeds, otherwise result error. And then we have to unwrap the result to get the value in the result. So in this case, we can use, So in this case, we can obviously use match. And so if it's okay, then we return the file, or we assign the file to the variable. Otherwise, in this case, we just panic if there's an error. Cool. And then similarly, one. And the nice thing that result allows us to do is to bubble errors. And so just walking through that. So oftentimes we don't want to handle the error where it's encountered because we don't have like full scope and full knowledge of what we're trying to do and what we're trying to achieve. And we also don't have context in those situations. And so instead, we want to propagate the error to the caller. So, and then the caller implements logic to handle the error as required. So the caller has obviously full scope and knowledge of what's going on and can decide, you know, in this context, I want to handle this error in this way. And in another context, I want to handle it in a different way, for instance. And so, yeah, the important thing is to be able to propagate those errors back to the caller. And so we can do this quite easily. So here we see we have this function init, which has a result with the unit type and an error. And then when we're creating this file, so we obviously match on the result type. If it's okay, we assign the file to the variable. Otherwise, we return an error. So we have like this early return that says, you know, I encountered this error, I'm returning it back to the caller, and the caller can then implement any logic to handle that. And so similarly here, and then at the bottom, we have this, we can kind of think about this as the call of the function in some executable code. And yeah, we're just matching on this function call. And so in this case, I mean, it's obviously super trivial, but if it's okay, then we do nothing. And if there's an error, then we panic and say it could not initialize in this situation. So irrecoverable errors. So irrecoverable errors are obviously errors that we can't recover from. And those tend to happen like when we encounter bugs. So we'll come across situations where basically what we're saying is that, hey, I don't know how to handle this situation. And I think that the best approach is to stop execution. And that again is important for cases where you want to, for instance, just stop invalid states from occurring. Cool, so this is an example that I've obviously shown before in previous images where in this case, we writing to a file saying, hey, Ferris. And if it's okay, do nothing. But in this error branch, we panic. And so when we panic, the program crashes at that point in time and just says, you know, there's nothing further I can do here. So cool. That's just like a quick overview of yeah, just error handling in Rust, super high level. And so yeah, making it ergonomic with Rust really emphasizes language ergonomics. I think it's one of the first things that I quite picked up just from the community when I started learning Rust, and this is obviously great. So in the sense, or in the case of errors, the ergonomics come from having several convenience methods or syntax to reduce error handling boilerplate. So an example of this is the try operator. So try, so for bubbling errors, it requires boilerplate due to that matching syntax. So we have to go like, you know, if you match and then if the result is okay, then you assign the variable, otherwise you return the error. And Rust so introduced the try operator, or the question mark operator, as I like to call it, as a solution to this to reduce the boilerplate. So in this case, you know, we have the matching syntax, and this is without trying, or without the try operator, sorry. And yeah, you know, similar things. So if it's okay, we assign that file, otherwise we return the error. So we can simplify this by using this try operator. And here we have file create, and then we have appended the question mark at the end. And so these two are functionally the same, they achieve the same goal. And so if you know, if the function succeeds, then the variable is assigned and execution continues, otherwise the error is returned early, basically. Unwrap is quite similar. So the same principle can be applied to panic, where we can reduce the amount of boilerplate that we write. And it's achieved through the unwrap function. In this case, yeah, obviously it'll automatically panic if an error is returned. So here we have this init function. And on the file create call, we call this function .unwrap. And that will basically fail if an error occurs, otherwise execution will continue. And so in this case, for instance, you know, we try to write to a file that we didn't have permission to, and so, you know, it panicked and the program crashed. So those are like some small things, and there's many more of them: expect, mapper, and many others. Yeah, I think like it's worth going over them and looking into them as you continue to write more and more Rust. I certainly will, since I only know a handful of them. But it just shows like Rust's commitment to ergonomics and really trying to make the language easy and fun to use and have a great developer experience. So making informative, this section just really ties in back to communication. So again, error handling is all about communicating to developers, you know, what's going on. And so, yeah, just going through that. Good errors are highly informative. They improve developer experience. I mean, I'm sure everyone has encountered, obviously, if you've been writing Rust, you've encountered the Rust compiler, and oftentimes, you know, it's just the best in class in terms of like the error reporting that's given, and it's such a huge quality of life improvement, and so that really improves the developer experience. It helps debug issues much faster. I'm sure you've all been in situations where like the error you've gotten doesn't really point to, you know, what's really happened, or it's very opaque. and doesn't really give you enough context. And you spend hours and hours and hours and hours trying to debug an issue that would have just been solved way easier if you got like a more informative error. And so again, talking about communication. And of course, they make developers happy. They make developers happy to get highly informative errors, but routing them, who knows? So yeah, when we're talking about informative errors, we've got to think about them in two types of ways, or in separate ways when it comes to an application or a library. So this just really has to do with how we structure errors and the kind of like role they play in each case. So for a library, yeah, it's important to create meaningful custom error types. So this is important because obviously your application works in a certain domain, and failures are represented within some certain domain. So we want to really capture like errors that happen in that domain with these custom error types. And again, being able to communicate to developers that these certain kinds of errors happen in this sort of context that we're in. Another thing is wrapping standard errors where necessary, which allows applications to differentiate between various errors. So you can imagine, for instance, that if you have two crates, crate A and B, and they both produce IO errors, for instance, you want to be able to differentiate if an IO error came from crate A or crate B, because IO errors are from the standard library, for instance, and if they came from crate A or crate B. And so we wrap them in our custom error types or our crate specific error types so that we can differentiate for applications. Custom errors should always implement the error tray from the standard library. This is just important because it allows compatibility within the ecosystem. So before, there was a popular crate called Failure, which had its own trait fail. And it caused a lot of like compatibility issues at the application level when we're trying to stitch different libraries together. And so we've kind of like iterated and settled on always implementing the error tray from the standard library, which just, again, improves the developer experience. And then ideally, errors in a library should never panic, or library should never panic. It's kind of against what you would expect for a library call to like crash your program. And so instead, we would want to return errors and the caller can then handle. Applications are a bit different. So in applications, they consume errors, and their task is to make informed decisions on how to handle those errors. So they're at the level where they obviously are operating in the context that they're in, and can decide how to handle certain situations depending on obviously what's happened. They can panic. So at the application level, if we come to a scenario that we don't know how to handle, it's easy to just say, raise hands and just panic and crash at that point. And they're also responsible for deciding how errors are formatted and displayed to users. So effectively, like how they're communicated to the user. So for an application, like adding context is extremely important. So walking through that, errors need to include the context in which they were generated. This provides developers clarity on the error case, and it improves our ability to discover and diagnose failure cases. So like, obviously there's the question of like, what does that mean? So just walking through an example sort of situation. So in this first case, we have this error, no such file or directory, which is not extremely informative. We don't really know, where it came from, or like where in the library, like where in the code it came from, what file or directory it was, whether it's a file or a directory. And so we're kind of like left open-ended with the fact that we just know we've got this. We try to do some IO operation, but there's not too much to that. So we can improve that, for instance, by adding, the file that we failed to read. So in this case, we get the error, failed to read file, which is ferris.txt. And this was caused again by this no such file or directory. So in this case, obviously what's nice is that we're able to say, which file we were trying to read and which one failed. And then in this case, we can augment this even more by adding, for instance, like a backtrace, just as an example. And so, that again adds more context and information to to the error report in this case. And then we can think of other things like, in this case, there's no location in the code where this error occurred, so we can add something like that. We could add a suggestion, for instance, like create the file ferris.txt. And so, in those cases, we can keep thinking about how we can make these error reports or error messages way more informative at the application level. And that adds context to what's happening. So for a library, custom errors, again, are the most important thing. Again, that model like your domain and communicate exactly the kinds of errors that happen in your domain. So just walking through an example again, in this case, we're just using this error, which is one of the like commonly used crates in the Rust ecosystem for creating like custom errors. And in this case, we have this beat maker error. So some of the errors that we have is like invalid notes, invalid format, and an invalid instrument name, whatever. And then an interesting one here is that we can wrap all IO errors from the standard library into like our own IO error type in our beat maker error. And so that just speaks to, again, that idea of wrapping errors so that we know that these IO errors came from like this beat maker library. So this is just a simple trivial case of using that error. So in this function called raise, we have a result which returns it or can have a beat maker error. And that's, in this case, just returned simply just for the sake of this. And here we just match on that function call. And so if it's okay, I mean, you write a letter and then we'll write a message. And if it's an error, then we're too lazy to write better errors. So here's your error. Cool. And then in this case, we have it for an IO error. So what's really cool here is that we can return an IO error from, in this case, like file.open or file open. And this returns like an IO error from a standard library, but because we've wrapped those errors, we can still return like a beat maker error. And so when we call this IO raise, in this case, we haven't like taken any knowledge of that into use, but we will know that that sort of IO error came from beat maker, and that allows us to basically handle like IO errors from different crates quite easily. Cool. And so, yeah, wrapping up towards a better future. So error reporting obviously can still be better, as with pretty much everything in life. And some ways we can kind of think about that is making nice to read error reports. So again, like the Rust compiler errors are like really great error reports. And that's like best in class and kind of like the future that we're thinking about, yeah. Providing suggestions to resolve errors as well. So that's again something that the Rust compiler does. And then just in general, like Jane Lisby's error library is a experimental library that serves as a test bed for pushing the boundary on error reporting. And so, yeah, I was just going through like two sort of like error reports that come from that library, which are really cool in my opinion. So in this case, we have an error and you know, it's like it just describes what's happened. So unable to read the config and then command exited. So we get like an error messages, then we get the location, which is something that I mentioned earlier that we can sort of like augment to our error messages. So in this case, we get this location, then we get the standard error, so no such file or directory. We get a backtrace, which is in this case really nicely formatted. And then at the end, we get a suggestion. So try using a file that exists next time, obviously. And that's really nice. Gives a lot of context and a lot of information as to what happened, and kind of gives you like all of the necessary pieces of information to go from the error report sort of like directly to fixing your error without having to do too much extra legwork, basically. And then just another cool example here, where in this case, we're chaining errors. So multiple errors happened, which is the first error that we got here. It also gives us the location. And in this case, then we get these chains of errors. So like the task could not be completed, the machine's unreadable or unreachable, sorry, and the file could not be passed, blah, blah, blah. And that's really cool. So now we've got this like really informative, again, error report that kind of like walks through, you know, this sequence of errors happened. And it's like nicely formatted and easy to read. And again, just reduces the amount of like extra legwork that you have to do to go from error report to debugging your issue or fixing your issue. So yeah, that's basically it. Thank you. So yeah, again, just the main thing about this talk, again, just highlighting that error handling really is about communication, and that's the end goal when we're writing errors in our libraries and applications, is really just to be able to tell or communicate to other developers like this is exactly what went wrong. Cool. Thank you.
Thank you, Senyo. We have a couple of questions coming up. So the first one is, how do you determine which error type E should be, whether it is an IO error or something else?
I'm not too sure I understand the question too well, but I mean, that would come from you, like obviously if a certain function call returns a certain error, then obviously you know that E is that error. Otherwise, you define them yourself and then can handle that logic depending on what you've chosen. I don't know if that answers the question well enough, but yeah.
All right, so the next question is, I try to use always expect instead of unwrap. Do you use unwrap often? Do you have an ad hoc heuristic to decide when to use expect or unwrap?
So for me, like and also I think just pushed by the Rust communities, like unwrap usually is only used for sort of like prototyping or when you just, when you're in sort of like development, but ideally you wouldn't use it ever really in production code. The only cases where I do know it's often used is when you don't expect something to occur and like there's pretty much like a guarantee, not even that you don't expect it to occur, when it should never occur or never does occur really. So if you have like a strong guarantee that this thing will always work, then you can just use .unwrap. But in those cases, I think using expect is probably better than unwrap, just in the event that something goes wrong. And then you do get like at least some sort of like error message back, basically. Cool.
Yes, so on feedback for the first question, yes, it was already answered during the presentation. And the last question we have so far is, do you have an opinion on the crate anyhow?
Oh, yeah. So I should have mentioned that. That was my mistake. So this error is really good for creating custom errors, and that's like for the library context, and anyhow is for like application. So with anyhow, that's also like another commonly used, really like great, I guess, crate used for application errors. And so that one obviously allows you to add like those with context, and that runs at the application level. So when your application fails for any reason, you get back a nice error report with your custom message, and then whatever error happened, that's from your library. So of course, yeah, like I really advise using it. Cool.
All right, I think that's all we have. Thank you, Senyo, for the presentation. That's all we have for the questions. Okay, so thank you, everyone. The last talk for the night would be building cryptocurrency derivative exchange with Rust. And this one will be given by Konstantin and Blas. They are from Collider. Collider is the first real-time settled cryptocurrency derivative exchange. Using the Bitcoin, traders can instantly open or close position without exposing themselves to excess counterparty risk or hefty transaction fees. So yes, Konstantin, Blas, up to you.
Thanks, Evans. Let me just share my screen. Awesome. Can everyone see my screen? My
Yep.
presentation. Sweet. Cool. Thanks, Evans, for the introduction. And this is pretty much a more applied talk about how Rust is used in practice in a business sort of environment. So yeah, I'm Konstantin. I'm the co-founder of Collider, and pretty much everything Evans said we do. It's not necessarily super important because it's a lot of like jargon that he threw in, and I don't expect anyone to understand what he said. And so the aim of this talk is basically to basically share our experience with Rust, our love-hate experience, because we have been used Rust sort of in production since pretty much day one. And yeah, so the talk is on building a derivative exchange in Rust. And first thing I want to say, it doesn't matter whether it's a derivative or an equity or stock exchange, the basis is the same. So I don't want you to be confused about derivatives. Basically, just forget it from now on. And also, I don't assume any knowledge of what an exchange is, because I guess it's also very specific to finance. So I'm just giving you a little primer on what an exchange is. And essentially what an exchange is, it's pretty much just, a database, which we call the order book, where buyers and sellers come together to make an exchange of any type of good. It could be a stock, but it could be like apples or oranges. It doesn't really matter. But pretty much you have a buyer and a seller, and one wants to basically buy apples, the other one wants to sell apples, right? So one wants to give the other person dollars, for example, and the other one wants to give apples for dollars. And this order book is pretty much just a place where they come together, and the task of the exchanges is pretty much matching these buyers and sellers together. So basically, making the price discovery of the sort of exchange. And when it happens, they match, and at that point, the exchange or the trade becomes finalized, and the two parties exchange sort of the goods, whatever it is, apples, oranges, doesn't matter. And then at that point, the exchange sort of gets a small cut from that transaction, and we call it exchange fees. And that is a very simple and beautiful business model, because the exchange always makes money, because it doesn't matter whether prices go up or down. They always take a small cut of the money. And you might be thinking now, awesome, I could do that. I just set up a exchange, get a couple people trading. It's awesome, because it's a very bulletproof business model. But sorry, that was actually I jumped the slide ahead. But yeah, this business model, it attracts a lot of people because it's so simple and beautiful in a way, and that's basically is the reason why the cryptocurrency derivative market is massive. Last year it tops $3.5 trillion in volume, which is basically saying that people traded $3.5 trillion with each other, which is amazing in a way. And that's just cryptocurrency. So financial markets, so traditional financial markets are not even included. Money, what I was going to say is that, this is great in a way. Everyone could just build an exchange and get people to trade. But, the truth of the matter is it's quite hard, actually. And that's sort of what we experienced, sort of first-handed. And why is it hard? Well, first off, you really have to process a lot of messages when people trade, and the whole process is really hard to parallelize. Just to give you an example of like a decent sort of like exchange, it's not even like a fast exchange. You have to be able to process 100,000 messages per second. You have to sustain a capacity of 5,000 orders per second, and your average trade latency, which means the time it takes from submission of the order to response, shouldn't take longer than 3 milliseconds. And that's basically wherever you are on the sort of in the world. And lots of money is on the line, which means you're dealing with with people's money. So you have to be precise, you have to be correct, you have to be deterministic in whatever you do. Just to give you a little example, the 5 largest exchanges in derivatives in crypto, they process $200 billion in transactions every day. So yeah, there's very small sort of margin of error. And another thing is that you have to guarantee fairness, auditability, and availability, and that's just to make sure people sort of come back, because you cannot allow people to queue jump, front running. You have to be audible, and that's because every transaction needs to be sort of traceable. That's again from a regulation part, but also in instances where your platform crashes, you have to basically be able to reverse every state in the system, and you have to be highly available, which what means that this platform has to run 24/7, 7 days a week, and it can never go down, because a second of sort of outage, that means you lose revenue, and you're constantly under attack, and that's because you are sort of a honeypot. You're dealing with a lot of money, you so have a lot of money, and people try to either steal it from you, or they try to game your system. If there's a little bug in it, you can imagine that a small bug, small transaction error can lead to like massive amounts of money, if you repeat it like millions of times. And there are many stories about these problems. So yeah, I'll hand you over to Blas to basically explain or share with you some problems that we face sort of running this platform.
Yes, so essentially trying to put in practice a bit all these points that Konstantin mentioned in terms of why it is so hard to build an exchange. I'd like to go a bit more lower level and explain some of these particular issues that we have been dealing with and why they are relevant to us, and also somehow how we try to go around them. So the first one is whenever we need to deal with money, accountancy, and everything, we have to think, okay, how we're going to model these accounts. And one of the problems that we do have is that floating point is first is not even, like the steps between each of the different points on the sort of the line. So you actually have to go into something that you control more and understand, which is in this case the decimal expression. But essentially that means that you're moving from a lot of good things that hardware gives you, and a lot of auditability and things that work across all platforms, and you somehow model your problem a bit more with hardware, software instead of hardware. And essentially a lot of things that you thought they were in a certain way, they're not necessarily like this. Also, you have sometimes issues with the library panicking, and it's funny because this is something we talked, it was mentioned before, the library shouldn't panic, but essentially this is an issue that we do have sometimes. And particularly something I wanted to mention is that when we think of floating point operations, one thing, they're constant time, so one can think of them as being free. But for us, it happened once that we were doing a benchmark. Let me show you the flame graph that we had on our benchmarking, and as you can see, I mean, this is one method, but it's quite important one, and you can see like on top of it appears all the time Rust decimal. That was one of the crates that we use, and particularly we saw the division operation was very, very expensive. And so then we started like investigating, and fortunately they submit a patch that actually changed our profile into you can see the after something a bit more what we expected, and we actually for this method were able to go 5 times faster, which actually was amazing. But essentially what I want to try to say again is that we do have problems in parts of the code that sometimes we don't even think that would be an issue, in terms of both the result, that it has to be like what we expect, but also the performance as well. Another problem that we face is that we need to somehow model parts of your system, or the system, so that we get this deterministic behavior. Why is that? Because we need to be able to guarantee some of the things that Konstantin mentioned, but also in terms of like nobody jumping the queue or having weird behavior, but also because we need to be able to go back in time in case something breaks, or also in order to be able to audit. So one of the tools that we use often is we replay the system, perhaps offline, in order to be able to get to a certain state and audit, okay, how is the engine looking at this point? What are the accounts? What are the transactions? What actually has been happening? And connected to this, we need this mechanism to be actually safe and fast, because we do this very often at times, and also this is a mechanism that we use in the case of going down. So whenever we need to actually recover from this event, we actually need to make this happen as fast as we can. And connected to high availability, it is the problem of how do we replicate the different parts of our system? How do we communicate between them? How do we ensure that there's only one leader? Because we cannot have two parts of the system in certain areas talking to the market, because then we duplicate, let's say, an order, and that's not what we want. So that actually poses a restriction on us in certain places of the code or the system where we cannot scale horizontally, but only vertically. And actually the last issue that we do have, I mean, as a sort of a common denominator is I/O latency, introduced by writing to the disk, writing to the database, going to the network. So we do need to think, how do we log? How do we persist data? Which databases do we use? How do we actually go to the database? How do we write? Because we can batch, for instance, but we need to be sure that when we batch, the data is actually being written. And if there was an issue, we need to understand where it broke and communicate back to the system so that we can recover properly. So why do we actually enjoy using Rust for solving all these problems? For us, testing is paramount. We sort of stand in every day on top of our tests. They are the ones who kind of give us the guarantees that the system performs the way we expect it to be. And both we find Rust, like writing integration tests and unit tests, is pretty nice. The same with benchmarking. Whenever we want to test some new feature or for regression, we find that the crates and the built-in support from Cargo and the language is pretty nice. We do use quite a lot interoperability from systems written in C or C++. That's also pretty nice because there's a ton of safe wrappers that work really well. We also make use heavily in certain cases of metaprogramming, particularly procedural macros. And I mean, downstream certainly a lot. It's a blessing. And I think something else we make, I mean, good use of is the fact that there's a lot of crypto primitives and libraries that are built natively from like directly in Rust. A case is, for example, the blockchain Solana that entirely works out of the box from the Rust client. A bit the ugly part is that, particularly for the disadvantages that we do have, is that for the industry in which we are, competitors and sort of the status quo is writing everything in Java and C++, and thereby we miss a lot of really performant and ergonomic libraries because they don't have necessarily clients written in Rust. There are some community available options, but very far away from the ones that are mainly supported by the libraries. The same we see with some core dependencies that we actually use. They do have low maintenance because sometimes it's just somebody did it as a hobby, and then we take it and we need to maintain it ourselves or rewrite it from scratch, but it's not necessarily the optimal, especially for a startup. And the last thing is that we run a nightly, and sometimes it is a bit more painful because we run bleeding edge, which gives us a lot of features, but that makes our builds break for apparently no reason. Of course, then we need to adjust the code, but it's been quite fine all in all. Yeah, and that's it. Thank you. We're looking for good people to join us. So if anybody wants to come in on board, please go to Collider XYZ.
Cool. Yeah, thanks. That is it for our talk.
Thank you, Konstantin. Thank you, Blas. This was a nice presentation on blockchain. Yes, thank you everyone for attending today. I think we are at the end of our meetup, and hopefully we want to see you next month and have a great time. And again, as a reminder, we are looking for speakers. If you have a topic or a project to show off here, we'll be happy and excited to hear from you. I haven't seen any questions on the chat for the last talk, but if you have questions before we close, I think this is the good time to ask.